In section 1.8, we reviewed graphing linear inequalities, just one single inequality where you would determine if you were going to have a dashed line or a solid line. We determined if you were going to shade above the line or below the line. In this section, we're going to talk about solving systems of linear inequalities. So with the systems, as we learned in Algebra 1 and Algebra 2, we want to find the region of the graph where the shadings overlap. All of those ordered pairs are the solution to our inequality system. So let's look at example 1. It says Gina Chuas has considered starting her own custom greeting card business with an initial startup cost of $1,500. She figures it will cost 45 cents to produce each card. In order to remain competitive with the larger greeting card companies, Gina must sell her cards for no more than $1.70 each. To make a profit, her income must exceed her costs. How many cards must she sell before making a profit? We did a problem similar to this in a different section. When you have cost for a business and you want to make a profit, we have something called the break-even point. And the break-even point is going to be the point of intersection of the two equations. But these really aren't equations because my cost is going to be greater than or equal to, because I have a minimum cost. It's going to be 45 cents per card, and we'll call X the number of cards, plus the $1,500 I have to use to start it up. But I can't sell my cards for more than $1.70, so the amount of money I make has to be less than or equal to $1.70x. Remember, no more than means less than or equal to. The problem with the other inequality was they didn't use any of the words we learned in Algebra 1 or Algebra 2 to determine if it should be greater than or equal to or not. You just need to know that in business, the cost that you pay out, there's going to be a minimum amount of money that you're going to pay, and everything is going to be greater than that. Now, when I go graph this on the graphing calculator, if you have an older calculator, like an old operating system TI-84 or a TI-83 like I'm using here, in order to graph inequalities, you need to change this little line in front of y equals. In order to do that, you just move your cursor all the way to the left, and then you press enter. These little triangles that will eventually pop up are the triangles we use for greater than or less than. This is the one we use for greater than. Think about it like that. It's not quite pointing to the right, it's kind of pointing up and to the right. And then this is the one we use for less than. It's kind of like that. So when you graph it on the calculator, this is what you see. Now mind you, I did change the window, and I'll show you what I changed it to in a minute. But you can see that the shading seems to overlap up in here. And then there's some point of intersection that I'm not sure what it is yet, but I can find it by using second trace 5, enter, 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 and it'll tell me the point of intersection is at 1200, 2040. That's the break-even point. I need to sell 1,200 cards, and when I make $2,040, I will have made as much money as I've had to dish out to start this company. If you have a newer version of the graphing calculator, one with the new operating system, you can actually use a function called inequals to change these. But either way, unless you know how to change the window, this problem isn't very useful. So let me show you what I changed the window to. First of all, since this is a real-world problem, all real-world problems end up in the first quadrant. Particularly in this problem because you can't make negative money and you can't sell negative cards. So I made my X minimum and Y minimum 0. But how did I know what to change these to? One of my inequalities had a y-intercept of 1500. So I had to make my y maximum bigger than 1500. And I actually started with 2000, and then I ended up bumping up to 3000 so I could see the graph better. For the x maximum, I wasn't sure what to start with, but since the y maximum I changed to be in thousands, I decided I'd change the x maximum to be in thousands. And again, I started with 1,000, and I thought, well, I couldn't see it all, so I changed it to 2,000. What looked way nicer was when I did this on Desmos. And the cool thing about Desmos is you can type in the inequality symbols, and then you can graph this, and then you can just kind of use the mouse to zoom in or zoom out. And so I zoomed out until I saw the point of intersection. So you can see where the graphs overlap, because one graph has red shading, one has blue shading, so when they overlap it's purple. And then if you tap the mouse where it intersects, the point of intersection pops up, and you find out it's 1200 and 2040. So the question to the original problem, which seems like it was forever ago, was how many cards must she sell to make a profit? Well, if her break-even point, she sells 1,200 cards, to make a profit, she's going to have to sell more than that. So the number of cards, which is X actually, the number of cards she sells has to be greater than 1,200. So we're going to do something more with a system of inequalities than we've done before. You may or may not have done this in Algebra 2, depending on who your teacher was. In example 2, we're going to graph and find the vertices of the polygonal convex set. Let me rephrase that in layman's terms. We're going to graph these three inequalities. We're going to find the shaded region, and the shaded region is going to form a shape, just something geometric. We're going to be able to find the ordered pairs of the vertices of that shape. All right, so let's graph this. The first inequality, y is greater than or equal to negative 1/2 x plus 1. The y-intercept is 1, so I'm going to put a dot on 1. And the slope is negative 1/2. So in order to plot more points, we're going to go down 1 to the right 2, down 1 to the right 2, down 1 to the right 2. I'm going to go up 1 to the left 2 as well, just so I can make sure I have some nice points on the line. Because the inequality symbol is greater than or equal to, it's going to be a solid line through those points. And the shading is going to be above the line, because that's what greater than means. And I want you to notice that I didn't shade it. I just drew some arrows to remind myself which side the line gets shaded. Remember, you can also test a point, like 0, 0. 0, 0 is below the line, and if you plug in 0 for x and 0 for y, you find out that you get 0 is greater than or equal to 1, which it's not. It's false. That means everything below the line is false. The shading must be above the line. All right, so now let's graph the next inequality, and I'm going to do that in a different color. Y is less than or equal to negative 3x plus 5. The y-intercept is 5, the slope is negative 3, so I'm going to go down 3 to the right 1, down 3 to the right 1, down 3 to the right 1. I'm going to go up 3 to the left 1, just so I have a nice line. It is again solid. And less than, notice that it's pointing to the left, the shading is going to be this way. So right now, if I were to shade the intersection, it would be in here. But I'm going to erase that because we're not shading there yet. We need to do one more line. Y is less than or equal to 2x plus 2. The y-intercept is 2. The slope is 2 over 1. So I go up 2 to the right 1, up 2 to the right 1. I'm going to go down 2 to the left 1 as well. It is again a solid line. And I want you to notice that the inequality symbol is less than. Now here's the thing. You may think that, oh, it's pointing to the left, so I'm going to shade to the left. But that's not what less than means. Less than means shade below the line. And this is actually below the line. And what you'll notice is that the shading intersects in this triangle. So we want to find the vertices, and in general, a lot of the problems we're going to give you will have nice vertices where they intersect at integers. But you can kind of tell by looking at this one that the vertices of that triangle aren't necessarily at integers. Well, let me show you what this graph looks like if you had done it on the graphing calculator. It just looks kind of like a mess. I mean, you can probably see that there's this little triangle in here where the shadings overlap, but it's just kind of garbledy-gook. So the graphing calculator, although is often helpful, doesn't always get us to where we want to be. You can't just graph this on the calculator and get a nice graph like we got when we did it by hand. However, I do want to find the vertices. I want to find where these 3 points of intersection are. If you use the intersect function, you can find points of intersection as long as you watch what line your cursor is on. And that's something that I'm going to have to show you in class. It doesn't work well here in this video. But Desmos will make this a lot easier for us. If you go to Desmos and graph these 3 inequalities, you can click with the mouse on those 3 points at the vertices, and it'll tell you the points of intersection, which happen to be 0.6, 3.2, negative 0.4, 1.2, and 1.6, 0.2. The last thing we're going to talk about that's going to lead us into a practical application of systems of linear inequalities is called finding minimums and maximums using a given function. So this equation at the top of the page is pronounced f of xy equals 2x minus y. It's a regular old equation, it's just that we're going to input both an x and a y value. In other words, we're going to graph these 4 inequalities. We're going to find where the shaded region all overlap. We're going to find the vertices of that shaded region. And we're going to plug those ordered pairs into this top function in order to find out which ordered pairs give a maximum of the function and which give a minimum of the function. The function at the top does not get graphed. It's an equation that gets plugged into later. All right, let's look at the first inequality, which is y is less than or equal to 4x plus 6. The y-intercept is 6, and the slope was 4 over 1, so 1, 2, 3, up 4 to the right 1, but I'm running out of space, so how about I go the other direction? Down 4 to the left 1, down 4 to the left 1, down 4 to the left 1. Okay, there's my line. Not very well drawn, but it's there. And the shading, because it says less than or equal to, is below the line, and you may not believe it, but this is below the line. If you're unsure of which side to shade, remember you can test a point. 0, 0 is kind of to the right of the line. If I plug in 0 for x and 0 for y, is this true or false? Well, it's true. That means that everything on this side of the line is true. The second inequality, if you put it in slope-intercept form, you get y is less than or equal to negative 1/4 x plus 7/4. Let's change that a little. That's not a very good equation to graph, is it? Because the y-intercept, where do you put 7/4? I don't know. So what I did was I plugged this in the calculator, and then I used the table function to find integer ordered pairs that I could graph. So for example, I found 3, 1, 7, 0. I'll go back the other way. I got negative 1, 2. So those are some good ordered pairs on the line. And again, I just used the graphing calculator. So let's see, 3, 1 is here. 7, 0 is here, and negative 1, 2 is here. Hey, look, there they intersect at a nice point. And then the inequality symbol is less than or equal to. That means I'm going to shade below the line. So right now, the shading is intersecting here. Let's go to the next line. 2x plus y is less than or equal to 7. So y is less than or equal to negative 2x plus 7. That one is easily graphable. The y-intercept is 7, and the slope is negative 2. So I'm going to go down 2 to the right one, down 2 to the right one. I'm going to do that several times. Look, it hits another point. I'm going to draw my line here. And then I'm going to figure out which side of the line gets shaded. Less than or equal to, below the line. If you're not sure what side's below the line, check 0, 0. And you'll end up with 0 is less than or equal to 7, which is true, which means it is this side of the line. So now I can tell the shadings right now are all overlapping down here. But I still have one more graph to put on the coordinate plane. All right, the last one. X minus 6y is less than or equal to 10. If I put that in slope-intercept form, I have to subtract the x, and then I get to divide everything by negative 6, but it's an inequality, so guess what you have to do when you multiply or divide an inequality by a negative? You got to flip the sign, and you get 1 6x plus negative or minus 5/3. I don't like that y-intercept. So I'm going to put this in the graphing calculator, and then I'm going to use the table function to help me find some nice integer ordered pairs. So I see that 4, negative 1 is on the graph. I see that negative 2, negative 2 is on the graph. Let's see what else I can find. I found negative 8, negative 3, and I bet there's another positive one I can find here. 10, 0. So 10, 0 is on the graph, 4, negative 1 is on the graph, negative 2 is on the graph, and negative 8, negative 3 is on the graph. So it looks like the line looks like this. When it's in slope-intercept form, the inequality tells you to shade above or below the line. In this case, it's above. And now I can tell that all of my shadings are going to overlap here in this quadrilateral. At what ordered pairs do they intersect? Well, it looks like this is at negative 1, 2. This is at 3, 1. This is at 4, negative 1. And this is at negative 2, negative 2. Those are the vertices of the polygonal convex set. Well, now I'm going to go back to that function at the top, which I'm actually going to just rewrite down here. F of xy is equal to 2x minus y. In order to find which ordered pair maximizes the function and which minimizes the function, we're going to plug each of those ordered pairs into that function. So, if I plug in negative 1, negative 2, that's not negative 2, it's negative 1, positive 2. I get negative 2 minus 2, which is negative 4. That's the value of the function. Now I'm going to plug in 3, 1. So 2 times 3 minus 1 is going to be 5. Now I'm going to plug in negative 2, negative 2. So 2 times negative 2 minus negative 2, which is negative 4 plus 2 is negative 2. And now I'm going to plug in 4, negative 1. So 2 times 4 minus negative 1 is going to be 9. This is the ordered pair that maximizes the function because it's the biggest number. And this is the ordered pair that minimizes the function because it's the smallest value. So the maximum value is 9 and the minimum value is 4. I could have used Desmos to help me out and the graph would have looked a little bit nicer. And then I would have just clicked on the points of intersection. It would have told them to me, but I found them by graphing it by hand. as well. What we're going to be doing in the next section is we're going to be given real-world application problems where we're going to graph inequalities that are not easy to graph by hand, and finding the points of intersection of shaded regions and plugging them into profit equations to find how I can get my maximum profit or my minimum cost.